which was in the 84, so 25 years ago. If the Milky Way is spinning faster, it's spinning because of gravity. You need more mass then in the Milky Way to make it spin faster. Most of the mass in the Milky Way, if you talk to theoreticians and from various observational data, has to come from dark matter, not from stars, not from dust, not from gas. And the simplest models for how galaxies are put together, basically you can take this rotation speed almost at any place, because it's essentially almost constant as you go outward. I'll show you a plot in just a second. And you can compute the mass and the size from that speed. And so it turns out that the mass goes up as the cube of this velocity. So even though it's only a 15% change, you get about a 50% increase in the mass, mostly dark matter, in the Milky Way. And about 15% in the size of the dark matter halo, which is about 10 times bigger than stars that you can see in the Milky Way. So this dark matter halo extends way far out in the Milky Way. Let's not worry about that number. Oh yeah, we said that. Okay, so here's a plot of this information that I just told you about the rotation speed of the Milky Way. So on the vertical axis we have rotation speed. This is 100, 200, 300 kilometers per second for the Milky Way, as a function of radius. So if you're at the galactic center, you'd be at 0, which would be about here. We can't make measurements in there very accurately. But if you're 8 kiloparsecs from the galactic center, or 8.4, which is about where we think the sun is, we've measured a rotation speed of 254 kilometers per second. We could also, from modeling all this data, get what's called the slope of the rotation curve, which are these lines here. And basically we find it's probably within those two lines. That is, the rotation speed is a function of radius in the Milky Way. Once you get a few kiloparsecs out, is nearly constant, maybe slightly rising, meaning it rotates a little faster as you go outward.
It's counterintuitive, though. Typically in gravitationally bounded systems, they would be slower.
Yeah, if you have just the sun, and you look at the Earth, what is its orbital speed, and then you go farther out to Jupiter, what's its orbital speed, it will drop off as 1 over square root of distance. So to have a rotation curve that doesn't drop like that is more or less flat, means as you go outward there has to be more mass enclosed. So basically the orbits of planets in the solar system are totally dominated by the mass of the sun. But let's say there was a lot of mass in between the sun and the Earth and Jupiter, comparable to a solar mass or more. Then as you go out farther, inside you see more mass, and so you'll orbit faster. And so basically mass has to go up as linearly with distance. The total enclosed mass within any radius is proportional to radius in a galaxy. And ultimately most of that turns out to be dark matter. So here's, in blue, is the rotation curve information for the Milky Way that we get by fitting all our data. In red or purple there is data measured from the Andromeda Galaxy, M31. It's actually pretty easy to do it for another galaxy. You look at another galaxy, you see Andromeda out there, you measure Doppler shifts, for example, from hydrogen at radio wavelengths, or you can measure optical velocities of stars or gas. And you can see, okay, on this side it's blue shifted, on this side it's red shifted, therefore the galaxy is spinning. You can measure the spin rate as a function of radius from the center of the Andromeda. One thing you do need to know is the tilt, the orientation of the disk of Andromeda. But that's pretty easily measured too, just from its shape. And so this is the rotation curve for Andromeda, and you can see in the region we've made measurements here, they're virtually identical. Whereas the IAU value would have had the Milky Way down here at 220, significantly lower than Andromeda. So, basically this is the picture we had until a few years ago. That here's the Andromeda Galaxy in 31, roughly its size depicted by how big this picture is. And the Milky Way was the little sister of the Andromeda Galaxy in what's called the local group of galaxies. There are two big galaxies, the Milky Way and Andromeda, and lots of these little things like the Magellanic Clouds and other dwarf galaxies that are orbiting the Milky Way and Andromeda both. So these are the two big sisters here. And Andromeda is thought to be the big sister and the Milky Way the little sister. But from these measurements, it certainly looks like this is the better picture. The Milky Way and Andromeda are roughly comparable in size and mass. And so basically, instead of considering the Milky Way as the little sister of the Andromeda Nebula, I think it's better to consider them as fraternal twins. They certainly aren't the same. They have vastly different characteristics, but they have about the same size and mass.
No bar.
Sorry?
No bar.
No, Andromeda does not have a bar. Milky Way probably has a bar. Pretty good evidence for that. Andromeda has a very big bulge in the center of old stars. And the Milky Way has a bulge, but not as big. There are differences, so they're not identical twins, for sure. But, they're fraternal twins. Yeah.
I've read, or I've always believed from reading, that the Andromeda Galaxy is moving towards the Milky Way.
Yes.
But if they're about the same mass or the same size, they would just be together moving towards the center of gravity. Some central point of gravity between the battery point, right?
Yeah, but even if they're different mass, they're still moving together.
They're moving together.
Yeah, and they will hit each other probably. Now. Okay, now. Okay, we measure the Doppler shift of Andromeda Galaxy, which is its motion along the line of sight. We have not measured its proper motion on the sky. We would very much dearly like to do that. We have actually, there's a satellite of Andromeda, M33. It's a nice sort of small, spirally galaxy. And we've actually measured, that's another talk actually here, but we've actually measured the spin of M33. So we're capable of measuring motions of nearby galaxies, and we have actually done that relative to distant quasars. So what we need to do, there is a weak radio source at the center of Andromeda. It's got a black hole, roughly 10 times the mass of our black hole at the center of our Milky Way. Around this black hole is a lot of stuff going on, a lot of electrons spiraling around magnetic fields, emitting radio waves. And so we are going to try to measure that. Unfortunately, it's weak. And with the current telescopes we have and the current recording techniques, it's just a marginal observation. And so it's just not good enough for us to do. But we're upgrading our recording techniques dramatically. You can imagine digital advances in computers and everything. And so we can, if we can record data faster, which we can now, we can get more signal to noise.
Obviously, that is the brightest radio source in Andromeda, is the one
Yes.
with the nucleus.
Yeah, now what I haven't said through this talk is most of these parallax measurements were made of massive star forming regions, but not by looking at young stars, but by looking at gas near very massive stars